Imagine, humanity organizes the absolute greatest neighborhood watch in history. Right? Just to lock up our deadliest enemy.
Yeah, a massive global effort.
Exactly. The streets are finally safe. So, we retire the watch, we put away all the gear. But the second we drop our guard, this new opportunistic burglar just quietly slips into the empty streets next door.
Which is, exactly what happened with our immune systems.
Right. So welcome to this custom-tailored deep dive. Today, our mission is to cut through all the noise and really understand the reality of MPox, which you probably know better as Monkeypox.
Right, formerly Monkeypox.
Yeah. And the absolute most crucial thing to grasp right off the bat here is that we are not dealing with some brand new, highly mutated superbug.
No, not at all. I mean, we are dealing with a really obscure virus from the 1950s that it managed to seize this massive global immunological blind spot.
Yeah.
It's a pathogen that's been, waiting in the wings for decades, basically exploiting a vulnerability that we essentially created ourselves by succeeding in another area of public health.
Which is a wild paradox.
Okay.
And to unpack this for you today, we are pulling from a really heavy stack of data. We've got the latest CDC clinical overview, the World Health Organization's official fact sheets, a really comprehensive 2024 review from the Journal of Tropical Medicine, and an epidemiological breakdown from Curious.
It's a lot of ground to cover.
It is.
Yeah.
We're going to explore how this virus, literally hacks your immune system, the repurposed Cold War-era drugs we are dragging out of stockpiles to fight it, and how artificial intelligence is suddenly becoming this vital tool in outbreak management.
Yeah, the AI aspect is fascinating.
It really is. But to understand why MPox is such a global threat today, we have to look back at that neighborhood watch analogy I mentioned. We have to look at, one of humanity's greatest medical triumphs ever, the eradication of smallpox back in 1980.
Right. The eradication of smallpox is really the turning point here, because both smallpox and MPox, they belong to the exact same family of viruses.
The orthopoxvirus genus, right.
Exactly, the orthopox virus genus. And because they're in the same family, they share a lot of the same structural proteins on their surface.
Okay, so they look similar to our bodies.
Yeah, exactly. So this meant that the global smallpox vaccination effort, it didn't just protect people from smallpox, it provided this broad cross-immunity against the entire orthopoxvirus family.
Oh, wow.
Yeah, the smallpox vaccine was essentially a master key that locked the door against MPox as well.
But then, once smallpox was eradicated in 1980, the global vaccination programs they stopped.
Yeah, the threat was gone.
Right, we stopped handing out the master key, meaning literally anyone born after 1980 basically has zero baseline immunity to this entire family of viruses.
Yep, and that right there is the immunological vacuum. We completely dropped our guard.
Wow.
And, if we trace the timeline, MPox was actually first discovered way back in 1958.
Right.
In a group of cynomolgus monkeys at a research facility in Copenhagen.
Which is why the name monkeypox stuck.
Right, even though monkeys aren't actually the primary natural carriers in the wild. They were just, the unfortunate animals it was first identified in.
Right. And then the first human case didn't even appear until 1970, I think.
Yeah.
A 9-month-old boy in the Democratic Republic of the Congo.
Yeah, the DRC.
And for decades after that,
Yeah.
It mostly just stayed in Central and West Africa, occasionally jumping from an infected animal like probably a rodent to a human.
Mostly sporadic spillovers, yeah.
But it didn't stay localized forever. The data actually highlights this deeply bizarre outbreak in the United States in 2003 that it really shows how fragile global borders are when it comes to pathogens.
Oh, yeah. The 2003 outbreak is just a perfect case study in, modern transmission networks.
It's crazy.
It really is. So Gambian giant rats were imported from Ghana for the exotic pet trade.
Just normal pet trade stuff.
Right. And they were housed at this pet distributor in Illinois, right alongside Native American prairie dogs.
Oh, man.
Yeah. So the virus jumped from the rats to the prairie dogs, and those prairie dogs were then sold as pets, eventually infecting 53 people across several states.
I mean, it's just wild to think about. A global supply chain for exotic pets bringing an African virus straight into, living rooms in the Midwest.
It really highlights how connected everything is.
Totally. But that 2003 outbreak, it was still fundamentally an animal-to-human spillover,
yes,
right?
Exactly.
The crisis we are facing right now is completely different.
Yeah.
We have shifted to sustained human-to-human transmission.
Which is a massive escalation.
Right. And this escalation is exactly why the WHO declared a public health emergency of international concern. Not just once, but twice, first in May 2022 and then again in August 2024.
Right. And to understand how it managed to spread across, over 120 countries, we really have to look at the physical architecture of the virus itself.
Let's get into it.
So it's a double-stranded DNA virus, and it is massive in the viral world. I mean, about 200 to 250 nanometers.
That's huge for a virus.
It is. Under an electron microscope, it actually looks like a brick.
A microscopic brick. And it comes in two distinct genetic variations, or clades, as the sources call them.
Right, clades.
There's clade fun, which is endemic to Central Africa, and this is the severe branch. Historically, it carried a case fatality rate of up to 10.6%.
Though, with modern optimal care, we've gotten that down to less than 0.5%.
Still, that's significant, and clade spreads through close day-to-day household contact and non-sexual routes.
Yeah.
But then there's clade 2, which is endemic to West Africa. This is the branch that caused that massive 2022 global outbreak, primarily transmitting through sexual networks, right?
Right.
And it has a much lower mortality rate of less than 0.1%.
Yeah, the divergence between these two clades is basically dictating global health policy right now. I mean, clade I is highly virulent, while clade Toddy's is significantly less lethal, but highly transmissible in specific networks.
But wait, I have to push back here. Because looking at the genetic sequencing data from our sources, there is only about a 0.5% genetic difference between clade Y and clade 2.
Yeah, it's a tiny difference on paper.
Right. I'm struggling to see how a microscopic, 0.5% tweak in the code completely alters how lethal the virus is and how it spreads.
It's fascinating, honestly. It all comes down to a concept called host response modifier genes.
Okay.
The virus isn't just carrying instructions on how to build more virus. It's actually carrying weapons designed to disable your specific immune defenses.
Like active countermeasures.
Exactly. And clade 2 is actually missing a specific gene called MPox.
MPox. So it's missing a piece of its own armor. What does MPox actually do in the body?
So MPox is a complement pathway inhibitor.
Okay, what does that mean?
The complement system is a cascade of proteins in your immune system that acts like a biological tagging and disposal mechanism.
Like a targeted hit squad.
Yeah, pretty much. It identifies a pathogen, tags it, and essentially punches holes in it to destroy it. MOPE stops that cascade.
Oh, wow.
Yeah, it literally cuts the tags off. So because clade 2 lacks this gene, your body's complement system can actually recognize it and fight it off much more effectively early on.
That makes total sense.
But clade TI has the MOPCE gene, meaning it actively disables your immune system's early warning mechanism.
Okay, that explains the lethality difference perfectly. And there's another evasion tactic both clades use that, honestly, it sounds almost like science fiction to me.
Oh, the A47R protein.
Yes. From what I understand, this protein mimics our own immune system's signaling molecules, which are called cytokines, right?
Right, cytokines.
And cytokines are basically the immune system's alarm bells. So A47R creates these fake receptors that just soak up those alarms before the rest of the immune system can even hear them.
Yeah, it's a process called competitive binding.
It's so clever.
It really is. The virus puts up a fake communications network. By sweeping up the cytokines, the virus essentially creates this zone of silence around itself.
Wow.
So it completely dodges detection while it replicates heavily in the bloodstream, which is a phase we call primary and secondary viremia.
Okay, so once that brick-shaped virus has, silenced the alarms and started replicating, what is the actual clinical reality for the patient? The timeline here is very specific.
Very specific, yeah.
There's an incubation period of 5 to 13 days where you feel totally fine. But then comes the prodromal phase fever, intense headache, severe back pain, and just this bone-deep fatigue.
And then the rash appears.
Right.
And the rash follows a very predictable biological clock. It doesn't just, appear as random blisters.
Yeah, the clinical descriptions translate into a really visual progression. Like, it starts macular, which means flat red sores on the skin.
Right.
Then it becomes papular,
Right.
raising up into solid bumps. Then vesicular, filling with a clear fluid, almost like a severe burn blister.
Yeah, exactly like a burn blister.
And then finally, it becomes pustular. The blisters fill with an opaque yellowish liquid, which is essentially just a graveyard of dead immune cells before eventually crusting over and falling off.
Yeah. And during the 2022 outbreak with clade 2, clinicians actually noted a shift in this presentation.
Oh, really? How so?
The rash often started in the anogenital area and just stayed localized there, which was a marked departure from the historical spread over the face and trunk that we typically saw with clade I in Central Africa.
But if a patient walks into a clinic with a fever and a blistery rash, my mind immediately goes to chickenpox, or like a severe case of herpes. or syphilis.
Absolutely.
How does a doctor actually know for sure they're dealing with MPox without just guessing?
Well, diagnostic mimicry is a massive hurdle here. It looks incredibly similar to those other diseases. But the key clinical differentiator, the major red flag separating Mpox from chickenpox or even smallpox, is lymphadenopathy.
Right, tender, swollen lymph nodes.
Yes, usually in the neck, the jaw, or the groin. And we're talking about swelling anywhere from 1 to 4 centimeters.
That's significant.
Very. I mean, lymph nodes are essentially the military bases of your immune system. Mpox triggers such a massive, chaotic immune response in the lymphoid tissue that they just swell significantly.
Makes sense.
Furthermore, clinicians face this compounding variable, which is concurrent infections.
Meaning you can have more than one thing at once.
Exactly. A patient might have Mpox and syphilis simultaneously, or Mpox and HIV. So diagnosing a common sexually transmitted infection absolutely does not rule out the presence of Mpox.
Right. And to get a definitive diagnosis, you can't just run a standard blood test, right? Because the viral load in the blood drops way too quickly.
Yeah, blood tests are basically useless at that stage.
So the gold standard is a PCR test. But unlike a standard nasal swab for a respiratory virus, a healthcare worker actually has to vigorously swab the rash crusts or the fluid inside the blister.
Yeah, because that is where the viral factories are concentrated. You absolutely need the DNA from the active lesion to confirm the diagnosis.
And getting that diagnosis right is so critical because the complications for high-risk groups are just brutal.
They really are.
I mean, most healthy adults recover in a few weeks, but for children, pregnant individuals, and the severely immunocompromised, the virus can spread systemically.
Yeah, the systemic spread is where it gets dangerous.
We're looking at secondary bacterial infections,
Mm-hmm.
myocarditis, where the virus causes inflammation in the heart muscle,
Right.
severe eye infections that can permanently scar the cornea and lead to blindness,
Mm-hmm.
and even neurological complications like acute disseminated encephalomyelitis, or ADEM,
Right.
which is essentially just severe brain and spinal cord inflammation.
Yeah, when the immune system fails to contain the virus to the skin, it just wreaks havoc on vital organs. Which brings us to a very harsh medical reality once that PCR test actually comes back positive.
Yeah, the treatments. Because there are actually no FDA-approved treatments specifically engineered for Mpox. We are fighting a modern, evolving virus. But to defend ourselves, we are literally prying open the Cold War-era stockpile and pulling out weapons designed for smallpox.
Exactly. Because the viruses are so closely related, we rely entirely on the smallpox arsenal.
Right.
For the vast majority of patients, the approach is purely supportive care, right? Cane management, hydration, treating those secondary skin infections.
Just managing the symptoms.
Right. But for the severe cases facing that systemic spread, we turn to antivirals like tecovirimat, which is widely known as TPOXX.
Okay, so reading the mechanism for TPOXX, it's really interesting. It doesn't just nuke the virus.
No.
It targets a very specific viral protein called VP37.
Correct.
The Mpox virus apparently needs VP37 to wrap itself in a protective lipid membrane so it can safely exit the infected host cell and travel to the next one.
Yes.
So TPOXX essentially strips the virus of its coat and traps it inside the cell.
That is a highly accurate way to visualize it, actually. It prevents viral egress.
Viral egress, got it.
Right. So the virus might replicate inside the cell, but it cannot break out to spread the infection through the rest of the body. It halts the progression of the disease, buying your immune system time to clear it.
That's amazing.
Yeah.
But if TPOXX isn't available, or, if the virus mutates around it, the alternative stockpile drugs get significantly rougher on the patient, don't they?
Unfortunately, yes, they are very harsh.
Like cidofovir. It halts viral DNA replication, but the sources say it is highly toxic to human kidneys.
Extremely toxic.
As the drug filters through the body, it struggles to distinguish between the viral DNA machinery and human kidney cell machinery.
Right.
And then there's brincidofovir, which was developed to be less damaging to the kidneys, but unfortunately carries a high risk of severe liver toxicity.
Yeah.
I mean, imagine being a doctor having to weigh the lesser of two evils there, stopping a lethal virus, while potentially damaging a major organ.
It is a delicate, often very dangerous balancing act, which is, exactly why prevention through vaccination is the ultimate goal here. And the evolution of our vaccine stockpile is actually a fascinating reflection of how our understanding of virology has advanced over the years.
Yeah, because there are 3 distinct generations of vaccines here.
Right.
The first generation was Dryvax. That's the one that actually eradicated smallpox, right?
Yes, the original.
but it was incredibly harsh and had severe side effects, so it was discontinued. Then we get to the second generation, ACAM 2000.
Right, so 8N2000 is highly effective, but it is a live, replication-competent vaccinia virus.
Okay, meaning it can multiply.
Exactly. Because it's a live virus, it carries intrinsic risks. It can cause myopericarditis, heart inflammation.
Yikes.
But more importantly, it absolutely cannot be given to people with severely compromised immune systems,
Right.
such as those with advanced HIV, because the live vaccine virus itself could replicate unchecked and cause a lethal infection.
Which is a huge problem when you look at the epidemiological data showing HIV co-infection rates in some MPox outbreaks hovering around 40%. You literally can't safely vaccinate almost half the at-risk population with HM2000.
It's a huge barrier.
So that necessitates the third-generation vaccine, JYN-NEOS.
Yes, JYN-NEOS.
And this one is a modified, non-replicating virus. It delivers the immunity, but the virus is biologically incapable of multiplying inside the human body. So it is incredibly safe, even for HIV-positive patients.
It's a massive step forward. But, you know, we are also seeing the bleeding edge of future therapeutics in development right now.
Oh, yeah.
Taking lessons from the COVID-19 pandemic, researchers are currently developing mRNA vaccines specifically targeted at MPox.
Which is great.
But perhaps the most conceptually fascinating development mentioned in the current literature is the use of biomimetic nanoparticles.
Okay, biomimetic nanoparticles. Let's break that down because it's wild. Scientists are engineering these microscopic artificial particles.
Yeah.
And they're coating them in the actual cell membranes of human macrophages, right?
Right, which are immune cells.
Yes,
Yeah.
immune cells. And the MPox virus naturally hunts for and binds to those specific immune cells. So when these coated nanoparticles are introduced into the bloodstream, they act as microscopic decoys. The virus binds to the artificial nanoparticle, thinking it's invading a human cell, and just gets permanently trapped.
It is cellular mimicry used as a weapon. The virus's own binding affinity is totally turned against it.
Nanotech decoys. I mean, it genuinely feels like the future of targeted treatment.
It really does.
But, you know, while mRNA and nanotech are the future of treating the disease inside the body, there is another technology rapidly becoming the future of diagnosing it out in the world.
Ah, yes.
And that is artificial intelligence.
Right, because outbreak management relies entirely on speed. In regions where PCR laboratories are scarce or just non-existent, AI is stepping in to fill a very critical diagnostic void.
Yeah, epidemiologists are deploying deep learning and convolutional neural networks models with names like MobileNet V2, VGG16, and vision transformers.
Right.
They are training these AI models to visually diagnose MPox just by analyzing photos of skin lesions. And it makes sense, right? A convolutional neural network acts like a hyper-focused detective. It looks at thousands of images and learns to spot these microscopic pixel patterns, the specific curvature of a blister or like a slight discoloration at the edge of a lesion. Things a tired human eye might easily just gloss over.
Absolutely. The highly visual phased nature of the MPox rash makes it just an ideal candidate for machine learning image analysis.
Okay, but I have to play the skeptic here for a second.
Sure.
Imagine a patient in a rural, low-resource clinic in the Democratic Republic of the Congo. Is an AI algorithm on a smartphone really practical?
I know, it sounds a bit out there.
Yeah, like they might not have reliable cellular data, let alone high-end technology. Is this just some Silicon Valley tech gimmick that looks good on paper but completely fails in the mud?
It's actually the exact opposite of a gimmick. It is a vital public health upgrade designed specifically for the mud.
Okay, how so?
Consider the logistics of a standard PCR test in a low-resource setting. A patient presents with a fever and a rash. To get a diagnosis, a healthcare worker swabs the lesion, puts it in a cooler, and that physical swab has to be transported literally hundreds of miles to a central laboratory.
Oh, wow.
Yeah, it might take days or even weeks to get a result.
And during those 2 weeks, the patient just goes back to their village and potentially infects dozens of people. The transmission window just stays wide open.
Precisely. The delay in diagnosis is the ultimate enemy of outbreak control.
Right.
But if a local healthcare worker can just take a photo with a basic smartphone and a lightweight offline AI model like MobileNet V2 can differentiate a monkeypox lesion from chickenpox with over 91% accuracy right there on the spot, the epidemiological math changes completely.
Wow, 91% offline. That's huge.
It's massive. It allows for immediate isolation. It triggers immediate contact tracing. Furthermore, it significantly reduces the severe financial burden on families who otherwise might, spend a month's wages traveling to a major healthcare facility just to be told they have a benign rash.
So it doesn't replace the doctor at all.
No, not at all. It scales the doctor's diagnostic expertise to the most remote corners of the earth.
That is just incredible. So bringing this all together for you, we've traced how MPox quietly capitalized on the immunological vacuum left behind after we locked away smallpox.
Right.
We explored its deeply complex virology, missing genes that drop lethality, and fake cytokine receptors designed to silence our immune alarms.
The A47R protein.
Right. We unpacked the biological clock of its clinical rash and the diagnostic nightmare of telling it apart from common infections. We look at the harsh realities of relying on toxic, Cold War-era smallpox drugs to treat severe cases and the incredible promise of non-replicating vaccines, nanotech decoys, and AI-driven smartphone diagnostics.
It really is a remarkable synthesis of virology, history, and cutting-edge technology.
Yeah.
But there is a lingering critical unknown that all of this data points toward.
Oh, what's that?
Well, we know that MPox originally jumped to humans from an animal reservoir.
Right.
But despite decades of research, the actual primary natural reservoir in the wild remains entirely unidentified.
Wait, really? We still don't know?
We suspect certain rodents, but we do not know for sure. And this raises a chilling thought for the future.
Okay.
If this virus continues to circulate and silently mutate in totally undetected wildlife populations deep in the forest, are our highly targeted AI diagnostics and our extremely specific mRNA vaccines only preparing us for the MPox of today? Are we leaving ourselves entirely blind to the MPox of tomorrow?
Wow. It's like the neighborhood watch finally got the security cameras installed and the decoys set up, but the burglar is already out in the woods next door, figuring out a completely new disguise.
Exactly.
Definitely something to mull over. Thank you for joining us on this deep dive, and we'll catch you on the next one.